headphone, which is different than this one. Okay, so welcome back, ya shabab. We are a little bit late with the material. I'm not gonna stress about it, honestly. Trying to move slowly. Hopefully, we meet the schedule very soon. We need to free up 4 slots for the quizzes, and that's why we are, we need to be a little bit careful. But I would rather make sure that you understand what I'm saying, and then inshallah, when we move further with the course, things will start to get more familiar, and we can probably speed up a little bit. So last class, ya shabab, we talked about this relation between life, load, and reliability. And we put it this way. We said simply, if you go to the industry, you will see that many people would require a reliability which is more than 90%, which means, you understand. Now, here the companies have a like one choice. I mean, 2 choices: either to say, I am not gonna do it for you, which is the case right now, or the other case, you say, no. What do you want? You want a 96% reliability, and then they go and perform all of their testing to produce that. They do the Weibull distribution and everything, and they test thousands and produce a new catalog. And then another client comes and say, no, I want 97. And then they repeat everything again. I say, I want 99. And then they repeat everything. No, there is no way they are going to do this. So what is happening is that they produce their catalogs, which by itself is a huge task. Okay, there are probably thousands of bearings, and for thousands of bearings, they need to test thousands of tests on something. So it is a lot of work. And so what happened is, as we discussed before in the last class, I'm just reminding you over here, is that there is the reliability constant line, which is, by the way, this line is as simple as a load, which is log F, and then life, which is log X. This is just like a stress life curve and fatigue of a 307. And the line is going this way. We told you before that the equation for this line is F, and then F X to the power 1 over A, which is equal to constant. Now, that particular line belongs to 90% reliability. The question is, what if I want a different reliability? That's the question. Now, look, the idea here is this. Be careful, for a catalog value C10 with a reliability of 90, you will hit the curve, and then you will go down, and you will know what is the dimensionless X10. X10 is probably 1, right? Because X is equal to the life, which is now here for 90%, it is 10 to the power 6, divided by L10, which is 10 to the power 6. You got that. Now, however, for desired load and for a desired life, you will get, for a desired reliability, you will get a desired life. Now, the question is this. You want the same desired life, the same desired load, but the reliability is different. You want a 99% reliability. And what happened here? You want to use a bearing which is rated for 90, huh? 90. So I told you the example last time as follows, very quick, is that if you have a load and you want 100 million cycle, for example, and the reliability in the catalog for 90% reliability in the catalog, they told you use 10 kilonewton rating. C10 equals to 10 kilonewton. If somebody asked and said, how about if I want 99%? And the load is the same. I mean, the desired load, be careful. The desired load is the load that you are applying. You said, I am not going to reduce the load. I'm not. My machine requires a load of 10,000 Newton. I'm not going to reduce it to increase the reliability. I want 100 million life. So what is the rating of the bearing that I should use? Be careful. You can use a bearing which is rated for 50 kilonewton, right? Your load is still 10,000. But if you use 50, how much is the reliability? Maybe it is 99.99999. You don't want that. And you are going to pay too much cost. You want 99. So maybe you need to use 30. So you want to know that, period. That's it. So what are we going to do is this. Since the desired curve over there, now look, since the desired curve over here, this one has 2 points. This point is the desired point. Point B, we don't want it, but it belongs to the desired reliability curve, and it has a special feature. It intersects with C10, the rating of the catalog. Why? Because in here, I am putting a constant life, a constant load curve. It intersects point B and it intersects point A. Yeah? Still, what are we going to do? Since these 2 points are on the same line, the equation fx to the power 1 over a, which is constant, can be used because the reliability is the same. So what are we going to do? We are going to write down the equation for point B, which is equal to point D. And by doing so, we can write what is FB. What does this mean? What is this force? By the way, FB is the same as C10. They are on the same line. So what is FB? If I know what is FD, which is the desired load, and I know the dimensionless desired life, as well as the dimensionless life for this point, which is the point that intersects the new reliability line with C10. Now, let's face it, ya shabab, you don't want to talk about point B. Point B was forced on you. You don't want it. Who wants to talk about point B? Point B has a catalog value of C10. It has a reliability which is desired, maybe 99, which is good, but its dimensionless life factor is less than what I want. I want to be here, not here. So I need to get rid of it. I need to get rid of it. How? Well, for a constant line, for a constant load line, which is this line. Let me again clean this diagram. I'll do this probably several times. This is the constant line. I can write the what, ya shabab? The reliability equation, which is RD, okay, the desired reliability equals to, okay, the exponent, and then I have the dimensionless life measure for point B, and then what do I have? I have the weighable parameters. Why? Because look, this point share the same load as this point. Now, look carefully. If I solve for XB, what do I get? I will get this. Now, if you look carefully here, this is the weighable parameter, and this one is the desired what? Reliability. Now, if I take this, okay, that's that. It doesn't show up quickly. If I take XP and I substitute it in here, look what will happen. I will get rid of everything related to B, which I don't want to. I told you from the beginning. So what would I have? I will have in the equation FD, which is my desired load. This what is the boss gonna tell you to have in the machine, in the company. And then a dimensionless measure of life that you want as a client, and weighable distribution for the manufacturer. You want Timken, SKF, whatever, this is tabulated for you. And look what happened. You will put the reliability, 99, 95, 96, anything you want. What is the end result? The end result is so beautiful. Why? Because you will obtain the corresponding force for point B. Now, force for point B is the same as C10, which is a catalog value. And this is where the magic happened. Look, this equation is what you want. It's a C10. From where did I get C10 all of a sudden? Because it is the same as FB. And FB is the same as C10. They are in the same line. So what happened? We here introduced a little factor called AF. This isn't gonna confuse you, don't worry. This AF is called the application factor. And its story is very simple. It is more or less similar to the safety factor. If you go to industries around, they will tell you probably for maybe, I'm just saying maybe, I don't know the numbers, for an elevator, you should use a factor of safety of 4 or 6. For a car, you should use a 3. For an application that involve, airplane or whatever, you should use 10. We don't know, but there is a general standard for a factor of safety. This is the same. I'm going to show you a table later which lists the application factors for different categories. Most of the times around 1.2. So this doesn't concern us now. This isn't what are we focused on. What do we want to focus on is this nice equation. This equation tells you if you have a desired load, your machine needs 3 kilonewton. You put 3 kilonewton here. No more, no less. And then your dimension life, what is it? XD is equal to L desired over L10. Is that right? Tell me, from which bearing companies you are gonna buy your bearing? Once you decide, you say, I'm gonna buy it from SKF. What is the catalog? The catalog, I have it here with me, and they say that their L10 is 10 million cycles. I know this. How much do you want as a company? You remember the story when I told you maybe after 5,000 hours, maybe after 2,000 hours. Yes, you need to convert. This one is in revolution, while this one is supposed to be maybe in hours, so you need to convert it. That's fine. But this is also known, it's under your control. What are x0, theta 0, and x0? They are, and b, by the way, they are the Weibull distribution factor, and these one should be, disclosed, informed from the, you get the info from the manufacturer. So what left here? What is your desired reliability? Put anything you want. The load, probably you cannot change it. Your machine requires a certain load. It requires a certain life. But how about the reliability? 1 in 100, which is 99%. 2 in 100, 2 chances of failure in 100, which is 98%. You decide. Once you decide, do you know what are you going to get? You're going to get a C10. C10, ya shabab, is the treasure. You just go to the catalog and look for C10, which is going to be suitable. That C10, what is it? C10 is going to be 25 kilonewton, 30 newton, 100 newton. I don't know. But that Newton, that rating tells you that, oh, I need to buy this bearing, not this one. That's the meaning of the C10. And when I use this bearing, it will give me 5,000 hours. It will give me a reliability of 99%. End of the story. Got it, ya shabab? So, if you recall, we said once that the reliability is equal to 1 minus what? The probability of failure. Isn't that true? So if you substitute 1 minus the probability of failure instead of the 1 over RD, you will end up with approximately ln 1 over RD equals to 1 minus RD. This is just a simplification. Okay, so equation 11.9 is the same as equation 11.10, but in here you don't have a natural logarithm. For whatever reason, is it easy to calculate or whatever? Now, there are a few hints that you need to understand over here. So you can use equation 11.9 or equation 11.10 to convert from a design situation with a desired load, life, and reliability. 3, to a catalog rating based on a rating life of 90% reliability. You get that? That's very powerful. Very powerful. Now, if you substitute RD in this equation as 0.9, this should put you back into the catalog reliability. And what will happen, you will realize if you do that, you will realize this denominator is going to approach 1. It's going to be like 0.99 something, which is nearly 1. And if this is 1, this equation will become C10, which is equal to AF. Remember that AF is like a factor of safety, so forget it. And then you will have FD multiplied by XD to the power 1 over A, which is the same equation as equation 11.3 we talked about before, which is very much right. Is that true? We're back to 90% reliability, so everything should be back to the catalog. I don't need, there is nothing here which is different. I am not requiring data which hasn't been tested for the, so ya shabab, listen, if you want 90% reliability, okay, and if the rated life you have is enough for you, then you should go to the catalog and pick C10, which is the same as the load that you demand for your application. The problem is this: you may have a different requirement of life, or طبعا يا شباب تذكرون, you remember, when we have different requirement for life, look, I'm gonna show you this just to connect the dots in your brain. This equation, why did we do it? Because we said you may want, and be careful, to change the load or to change the life. You understand? This will change the catalog value, but the reliability on the desire side and on the catalog side, both of them are 90. We did not talk here about reliability. So that's the difference. So that one is an advanced step. You understand? In here, we were only saying, oh, the catalog rated value is 10 to the power 6. You may want like 10 to the power 7. So what should you do? This is going to help you find the proper catalog value, which will serve for that purpose. But both reliabilities are the same. Okay.
Doctor.
So let's go back. We have an example. Sorry, this is going to spin your head. Yes. Go ahead.
So the reliability and the load should be constant, and the variable will be just the life. Or we can choose the opposite way. I know the life, but I don't know the load.
I hope I got your question right, but these two equations, the first equation that I showed you, okay, just a minute ago, for a catalog value on the right-hand side, and on the left-hand side, and on the right-hand side, a desired value. The desired value were either a load or life. The rating life is 10 to the power 6, as we said, in general, unless otherwise stated. And the catalog value for the force is tabulated: 1 Newton, 2 Newton, 3, that depends. So what is it? The manufacturer will make many bearings. All of them will serve a desired load of, for example, 10 Newton, 10 kilonewton, 100 Newton, whatever it is, for a certain rated speed. If the speed changes, you may need to change the catalog number because the speed is different. That's it. But all of them will give you a reliability of 90%. In this equation here, we are telling you, no, you can put any reliability you want, you can put any life you want, you can put any load you want, and in the end, I will tell you from the catalog which bearing should you pick. Understood? Remember, the catalog will always give you the catalog, ya shabab. When you go to the catalog, these values of the catalog are designed for a specific load, a specific speed, a specific reliability. Remember always that. Any bearing in the catalog corresponds to a specific speed, a specific load, a specific reliability. You cannot restrict the industry. You cannot. You go to oil industry, they want different thing. You go to gas industry, they want different thing. You go to aviation, they want different. Automotive, different thing. So what should we do? We need to have a mapping, something that makes everything, and tell me which proper value I should pick. Do you understand? Now, be careful. I'm going to tell you one thing, ya shabab. Let's say I have FD, and let's say I have RD, and let's say I have XD. This came from my boss. I cannot change them. The bearing I will pick, C10, okay? Be careful. This C10 has been rated for C10, which is a specific load, has been rated for X10, which is a specific dimensionless life measure, and has been rated for a 10 percentile reliability, which is 90%. However, you are going to use it for totally different applications. The idea is this: is this safe for you or not? And I gave you the example that you can easily amplify the capability of the bearing to obtain higher strength, higher reliability. The question is, by how much? This is the benefit of the equation. So be careful. When you use a bearing, it is rated for 90%. It is rated for 1 million revolution. It is rated for a specific speed and specific load, but you use it in different places for different loads, different speed, to give you different reliability. This has to be understood. So this is now the problem.
Question.
Yes.
So equation 11.3 is used for a specific load, for a desired load, and equation 11.9 is used to find a catalog rating for a desired reliability. Is that the difference?
Equation 11.3, which is f x to the power 1 over a equals to constant, is just a representation of this line for a given reliability.
No, C10 equals FD times LD and D60 over that formula.
This one. This one, you mean?
No, equation.
It's coming up.
The one in chapter 11.3, 11-3.
Okay. This equation.
Yeah, the other form of this equation, C10 equals FD times LDN. So this formula is when you want to find the catalog rating for a desired load.
A desired load and a desired speed.
Okay, and the other one is for a desired reliability.
Exactly. And in the package, you get to put your desired load and desired speed as well.
Okay.
All together. So that one is more comprehensive.
Yeah, okay, got it.
Okay. Good. Now, let's get this example quickly so we can move on. It says here, the design load, which is FD for a given bearing, is 413 pound force. The application factor, AF, is 1.2, which is suitable for that particular application. Now, the speed of the shaft, which is ND, is equal to 300 revolution per minute. The life in hours, kilo hours, not in revolution, so it is italic LD, is equal to 30,000. It is 30 kilo hours, and it is in hours, not in revolutions. Now, what do we want? We want a desired reliability of 0.99, of course. That's what probably people want always. What is the C10 catalog value for this? To give me a safe, delivery like this. That's something that give me this requirement from the catalog for a bearing, which is a deep groove bearing. The Weibull factor x0 is given to me. Theta minus x0 is also given to me. And B is given to me. So what I am going to do right now, I'm going to use this equation. I'm going to just write it down for you over here. C10 is equal to AF FD, and then I have XD divided by X0 plus theta minus X0. And then I have the ln of 1 over RD to the power 1 over B. And then be careful that here the power is 1 over A. So let's go over these one by one. AF is given to me. It is 1.2. What is FD? It's also given to me, 413. Right? Now, what is X0 is given by the catalog. All of this is also given. And RD is 0.99. What is B? B is also given to me, which is over there. It is 1.483. What is A? This says it is a deep groove ball bearing. So for ball bearing, A is equals to 3, if you remember. And A for a tapered bearing or cylindrical bearing is 10 over 3. Okay? Now, that's it. What's left? This guy. Now, this guy, be careful with it. XD here is equal to what? LD divided by L10. Now, L10 is rated as how much? 1,000,000. 1,000,000 revolution, not hours. So what I'm going to do, I'm going to have a 10 to the power 6. And then do you remember the conversion factor? For LD, which is what? 60 LD multiplied by ND. That's it. Where the 60 is the conversion factor, okay? And then italic LD, this one, is 30,000 hour, not 30, don't forget. And then what do we have? We have a rated speed of 300. 300, the unit is still the same, revolution per minute. If you substitute all of this in here, you will get this. So this is basically how we substituted how to calculate XD. So it is 60 LND. This is the 60. This is the 30,000. And this is the 300. So we divide it by 1,000,000. And there you go. You have 540. You substitute this in here. This is 3, which is 1 over 3. And these are all the other values. If you got this, you will have this value. Now, what does this mean? You go to the catalog for groove ball bearing, and you find the bearing which deliver a C10, a catalog rated force of 6,696 pound force. Now, this particular bearing, when it was rated for this load with a speed which is different than 300 and with a reliability which is different than 99. But if you use it for your application, which requires a speed of 300, a load of 414 and 13, okay, it will deliver 99% reliability. Got that, ya shabab?
Yes.
Okay. All right. Now, what happens if we always talk about bearing in general, ya shabab, bearings are going to be mounted on, shafts are going to be mounted in bearings, and shaft will be mounted at least in 2 bearings. In some other situation we will show you later, we might put double bearings on one side and double bearings on another side. Now, the each bearing has its own reliability. Maybe, sometimes you put a tapered bearing on one side and a ball bearing on another side. This one has a reliability. This one has a reliability. You may not be able even to match the reliability perfectly. So what happens? It's okay. You don't need to get upset. What you should understand is that the reliability of the shaft is going to be what? The multiplication of both reliabilities. So if you have one bearing with a reliability RA and another bearing with a reliability of RB, the reliability of everything is RA multiplied by RB. Remember, you don't need both bearings to fail in order for the machine to shut down. You just need one. So your reliability here will be multiplied. I need to fix this. This is the goal. It is a general rule that the goal reliability is actually the square root of both reliabilities, the multiplication of both reliabilities. Don't worry, inshallah, later we will have an example, we'll talk about them. Now, what do we want to talk about right now is another topic, which is, now, if you think about it, we spent last week and almost today of this week just trying to talk about the load. We introduced C10, and then we talked about the speed, and then we talked about the rated life, the 10% reliability, 90% reliability, the probability of failure, the Weibull distribution. Now you are getting better and better. But now let's go to the real life. In real life, in general, if there is a bearing like this, and we know, ya shabab, there was a question by a student, which was a very good question. He said, from where this load is going to come on the bearing? It's actually the reactions. And we will solve a problem, inshallah, next class, where the reactions of a shaft are actually coming from the existence of bearing. Those reactions are going to act on the bearing. So the bearing is going to be subjected to what we call a radial load. Now, what happens if the bearing got subjected to an axial load? Axial load is resulting from a thrust, or it causes thrust in another word. So someone would expect, ya shabab, that if we apply a little thrust, maybe nothing is going to happen, which is true. But the idea is this. Just think with me. What if I keep FR the same, and then the thrust load starts to increase and increase and increase and increase? Now, we either, ya shabab, go and try to find a way to see how much is FR with FA, both, these two might change. What are the different combination of FA and FR that will cause failure, right? Or another way, which is what we are going to discuss, is to find an equivalent measure, which we will call FE. FE, look, FE is a radial load. So this is going to be the same bearing with a load FE. Where is the axial load? Where is the radial load? Both of them were combined with one load. How? Did we take the square root, the resultant? No. What did we do? Imagine that we have a radial load of 5 kilonewton, and we introduce a thrust load of 1 kilonewton, and we put them together. And let's say we get a life of 1 million cycles. The question I'm going to ask you is this. When we put the radial and the axial together, we get 1 million. What is the radial load alone that if we apply, we are going to get 1 million cycles? That load is basically creating the same damage, but it is only radial. That one is the equivalent load. Do you understand that? So in order to establish this very well, we need to make a distinction. Bearings have two traces, right? One in the top, one in the middle, in the bottom, you know, in the inside. Depending on the application, sometimes the inner one rotate, like when you stick it to a shaft, and the outer one is fixed. In some other condition, maybe the inner one is fixed and the outer one is rotating. So what are we going to do? We are going to introduce a rotation factor V over there, which is defined such that V is equal to 1 if the inner ring rotates, the inner one. And V equals to 1.2 when the outer ring rotates. طبعا يا أخوان, you need to understand one thing. These things in this course are a lot. If you like them, it's good. If you don't like them, you have to survive it. Why? Because as you see, we are not deriving equations a lot. Many of the data are coming from testing, experience, and so on. You understand? So if you have a self-aligning bearing, it doesn't matter. This rotation factor doesn't make any difference. So it is always equals to 1. So by doing this, and again, I am asking here for your patience for a little while. Why are we doing this? But later, it will be good. Okay? So we are going to introduce two factors, Fe divided by V multiplied by Fr, and Fa divided by V multiplied by Fr. Remember, Fr is the radial load. V is the rotation factor. Let's assume it is 1. I'm forgetting. Just let's assume it is 1. What left is this divided by this, and this divided by this. So the game goes like that. If I apply both loads, look what happens. If I apply axial load, a little bit of axial load, Fa, and a radial load, and I run the test, and the sample fail, I will, which is the bearing, I will discover that the equivalent load that will produce the failure, if Fa is small, is going to be almost the same as Fr. So if Fe is the same as Fr and V is equal to 1, so I will have a very like 1,000.1 divided by 1,000, which is nearly 1,000. So if you keep increasing Fa a little bit, you may always get that the equivalent load that will produce the damage by both forces is almost the same as Fr. In that case, this Fe divided by Vfr is going to be equals to 1. Look at the data point. These are experimental points. However, we will reach one point here, which is called E. All of a sudden, Fa become more and more, and Fe divided by Fr is no longer equals to 1. And this is the relation we have here as a straight line. You understand? So what are we going to do? In order to make this relation dealing with Fa and dealing with Fr together, we are going to construct a relation from this understanding, this curve, where we have two equations, either a straight line, which is equals to 1, if we are less than E, or an equation which is y equals to A plus bx, a linear line, where the intercept here is x, if we are bigger than E. You understand? I need to stop over here, ya shabab. I'm going to ask you to wait because I will share my computer screen right now, and we will take the attendance. This is the method that we are going to follow, basically, to take the attendance even in the future. So I don't need to switch on my webcam. Let's return to the menu. Anyway, it doesn't matter. So, Yusuf, Yusuf, are you here, Yusuf?
Yes.
Okay. Majid Al-Abbad?
Yes, I'm here.
Hassan?
Yes, I'm here.
Abdul Rahman?
Yes, Abdurrahman Bahjan.
Al-Ba'jan?
Al-Bahjan.
Al-Bahjan, okay. Da'bous Muhammad?
Yes.
Okay, so him. Abdul Aziz?
Yes, Doctor.
Ahmed Dosari?
حاضر دكتور.
Abdullah Jamri?
Yes, Abdullah.
عبد الإله صح. خالد
موجود يا دكتور.
مصلح
موجود.
okay, so. سعود
Yes.
الحجاب عبد الله.
Yes. Yes.
سلمان وشاني
موجود.
فارس الجبرين
موجود دكتور.
طارق
موجود.
عمر المالكي.
موجود دكتور.
عمر are you here؟ مصطفى
موجود دكتور.
عمر علي.
يس موجود.
العمر اوكي. خالد العتيبي
موجود دكتور.
حسام
موجود يا دكتور.
هاشم
موجود.
سادة
موجود.
سلطان
موجود دكتور.
نايف
موجود دكتور.
محمد
Yes.
سويق عبد الله الزهراني.
يس.
مشعل
Yes.
جعفر
يس.
مؤيد came with the other class. علي علي are you here? Okay, not here. Hassan.
Yes, here.
Yeah, okay. Okay, thank you so much, Ishav. That's the end of the lecture. See you next class.
Doctor,
Yes.
I'm from the first section.
Did you send me an email?
No, but you said we can't attend this because of the meeting.
Okay. Yeah. The meeting that didn't happen. Yes, that's